Hello everyone, welcome to the first lecture of week 8 of the course Power Network Analysis, in which we continue our discussion on power flow analysis, specifically the classification of buses involved in power flow equations and the corresponding equations that we would need. In fact, we have seen some of these equations in the previous lecture also. And in the end of the previous lecture, we were discussing about one such classification of bus, which is load bus. So basically, why do we need this classification? What we have observed is that every bus in the power network will have at max two equations, which are alpha and beta. But every such bus can have four unknowns, two independent unknowns, which are voltage magnitude and the voltage phase angle with respect to a reference, and the corresponding two dependent controls, which are PI and QI, the injections at these buses. So we have to ensure consistency between the number of equations and number of unknowns before we solve power flow equations, and that's where the classification of buses are needed. And in fact, we have seen also that the demand PDI and QDI for a given load, they can be known from the load forecasting exercise. PGI, which is the generation of ith generator connected to bus I, this can be known from economic dispatch, and the corresponding voltage magnitude phasor can also be known from active power loss minimization via reactive power control or active power loss minimization or via power factor control or excitation control. So these quantities, they can be known for the generators and these could be known from loads. So can this information not be used to understand the classification of buses and bring in consistency between number of equations and number of unknowns? That's where the first load type or bus type, the load bus or PQ bus comes in, where there is definitely no generator connected to such a load bus. A load may or may not be connected. The bus may only have few incoming lines and few outgoing lines through which the power is getting transferred. And since there is no generator connected to such a load bus, the injection at the ith bus becomes simply the corresponding negative of PDI and QDI. Remember, injection for real power perspective is PGI minus PDI. So if generator is not present, this is 0. So PI is simply equal to minus PDI, and similarly QI becomes simply equal to minus QDI. And since the load bus results into two knowns, which are P and Q themselves, that's the reason why it is also called as a PQ bus. So every such PQ bus has two equations and two unknowns, with the unknowns being the voltage magnitude and phase angle for the corresponding ith bus voltage phasor. The next classification of bus, or before I go into that, so I'll just briefly explain this part a bit. A load may or may not be connected. So essentially, what I mean is there is one such bus in the network which has few incoming lines and few outgoing lines. There is no other device connected to this bus, then this bus could also be called as a load bus or a PQ bus. And since there is no injection at all, no external injection for this particular bus, the corresponding injections would simply be 0, and we would also call them to be zero injection buses or ZIB, often also known in abbreviated form in the literature. If there is any other device connected to such a zero injection bus, for example, a capacitor or for example, a synchronous condenser, then the notion becomes a little different, because this bus in a way now becomes a controllable bus wherein the voltage can be controlled, which is what leads us to the next category of buses. It has got various names. We would start with the name of generator bus and then understand in a few moments that why it is also called as a PV bus, why it is also called as a voltage control bus. So generator bus, as the name says, the bus in the network which has at least one generator connected to it will be called as the generator bus. And this bus, through which the generator is connected, may or may not have a load connected to it. So essentially, if I talk about from the perspective of real power injection, where PI is PGI minus PDI, PDI may be 0, may not be 0, but definitely PGI should not be 0 for a generator bus. PDI may exist, may not exist, but as long as generator is connected, this quantity should not be 0, and then those buses would be called as generator buses. And as we have seen in the previous lecture, that for generators, specifically synchronous generators, the terminal voltages of those buses can also be known through active power loss minimization, and this terminal voltage can be controlled or regulated through corresponding reactive power control or power factor excitation control. So the notion of voltage controlled bus would also become evident, because at such a bus where a generator is connected, specifically synchronous generator whose reactive power control can be regulated, it can also have variation or controllability from voltage, so it is also called as a voltage control bus. Lastly, since the voltage specifications can be known from active power loss minimization, so in a way the quantities which are known for such a generator bus essentially are the real power injection and the terminal voltage. So since P and V are known, it also is often known as a PV bus. So that's the reason why P and V in blue, they are known from corresponding economic dispatch, load forecasting or active power loss minimization. And since reactive power equation is when reactive power injection is not known a priori and only the real power injection is now known here. So we have alpha equation, which is the real power equation, and subscript PV essentially means that it is referring to the PV bus. The reactive power, so for a bus to remain as a PV bus, the voltage magnitude should remain fixed. That means the reactive power generation should be within its limit. Reactive power generation, if it is within its limit as per the capability curve, the generator can still maintain a terminal voltage while playing around with or while regulating its internal EMF through power factor control or excitation control, and for that reactive power limits should be within the respective min max limits as per the capability curve. In case the PV bus or generator loses its reactive power control capability, that means the capability curve boundary points have been reached, terminal voltage will no more remain a fixed quantity and it should now become a different type of bus. So we will see that, what that different bus is. For a PV bus, P and VI are known, only unknown is theta I. So essentially for every PV bus, we have only one equation and we have only one unknown. We don't sort of exclusively solve the reactive power equation, because reactive power equation can be solved only when the injection at the PV bus is known. The injection can be known only when QDI can be known from load forecasting, but QGI has to be known, and QGI it has to be within a limit. It need not be a fixed number. So how do we ensure that? How do we sort of cater to reactive power equation? So we'll see that in the next slide. So just to summarize, for every PV bus, we only have the real power equation because P is known, terminal voltage is known from active power loss minimization. We have one equation and we have only one unknown for the PV bus. And as mentioned, terminal voltage is sort of known from active power loss minimization. It is assumed to be fixed. So for this voltage to remain fixed, as I stated, the reactive power generation should be within its limit. So how do I find the reactive power generation? I can rewrite this equation as QGI equal to QI plus QDI. QDI is known from load forecasting. I also know the expression of QI from the beta equation. So in order to sort of ensure that whether this QGI remains within its minimum or maximum limit as defined by the capability curve of the generator or the reactive power control which is available in the synchronous generator, I can probably make use of the latest voltage solution, find the reactive power injection through using equation beta and put in this number here and find QGI. If QGI happens to be within this limit, voltage magnitude can remain fixed. If not, then something else needs to be done. So what do we do for known voltages? These could be intermediate voltages, final voltages, or any intermediate solution that has come up while solving power flow. For known voltages, we find the injection using equation beta, and using QI plus QDI as the injection, as the generation, we then can find the reactive power generation at every such bus. If it is within the limit as defined by the capability curve as specified by the manufacturer, then the voltage magnitude can remain fixed, nothing else needs to be done. The PV bus would remain as a PV bus. If it doesn't remain within its limit, that means the generator or the synchronous generator has lost reactive power control, which means that either QGI is more than QGI maximum or QGI is less than QGI minimum as per this equation that we have evaluated. But these limits which are there, maximum limit and minimum limit, they are as per the capability curve, and it's unsafe for the generator to generate this quantum of reactive power. So what do? We don't allow the generator to generate beyond maximum limit or minimum limit. What we do is, in this case, we cap the generation to its maximum value or to its minimum value depending on the violation which is going to happen. And these points, when they are set, they essentially determine or indicate points on the boundary of the capability curve wherein no more voltage control can be done. So if voltage control can't be done, then it is expected that the terminal voltage will also no more remain fixed. In a way, by capping these generation values to minimum or maximum limit, we are indirectly fixing the reactive injection at every such PV bus. And remember, in a PQ bus, P and Q are known quantities. If voltage is no more fixed in a PV bus, it has to become a new variable. So we have two equations coming in for every such PQ bus or converted PV to PQ bus, which are alpha and beta equation, and we get two more unknowns, Vi and theta I, like the PQ bus. So that's where the PV bus gets converted to PQ bus. Because the reactive power control is lost, generator should not generate beyond maximum value or below the minimum value for safety reasons. The third category of bus, which is usually one bus or combination of buses, is called as the slack bus. Remember, when we say that the voltage has to be measured with respect to a reference, the reference was inherently chosen as the neutral point or the ground, which is all okay from the perspective of evaluating these equations. But if we look a bit more specific, that is, if we look at alpha and beta equations and think of what are the arguments of the sine function and the cosine function, both these arguments are the same number, which is essentially difference of phase angles of voltage phase angles of two connected buses. When every alpha and beta equation consists of difference of voltage of phase angles, and if we try to solve these voltage phase angles, we would find that at best we can find the value of theta k minus theta I. This can become known from power flow. That means difference of voltage phase angles can be known. It is almost difficult to find actual theta and theta k and theta I. The difference of theta k, or basically if I were to say, what we are trying to get here is we are able to find difference of two numbers from power flow analysis. Our purpose is to find these two numbers uniquely. To find these numbers uniquely, one has to choose one of these phase angles again as a reference. This reference need not be same as the reference of the ground or neutral. So basically, if we choose a bus whose voltage phase angle is chosen as some fixed quantity, for convenience sake, that number often turns out to be 0 degrees or 0 radians, although the phase angle could be any other real number, then that choice of angle for a particular bus helps in finding out remaining other phase angles and not just the difference of phase angles. And that's the reason why the last category of bus is also known as angle reference bus. Power flow analysis, as given here, can give values of phase differences and not actual voltage phase angles. Voltage phase angle of slack bus, we choose it to be some number which is known to be fixed, and once the phase angle of the reference bus is fixed, it helps in evaluating other voltage phase angles through these differences. That is one purpose of angle reference bus. It is also called as the slack bus. So basically for every such slack bus or swing bus or angle reference bus, the phase angle is fixed or chosen. It is not known from some numerical analysis. We as power engineer or operators, we choose it to be some number. Generally 0 number is a convenient number. Although it need not always be 0, it could be any other real number like 5 degrees, 1 degree, minus 2 degree, minus 3 degree, etc., etc. And the terminal voltage or the voltage magnitude of this angle reference bus is also known. In fact, the choice or the notion of calling it as a swing bus is because of the fact that among the generator buses or among the PV buses, we choose one of those buses to be a angle reference bus or swing bus. The value of PGI is intently not specified for this swing bus which is having a generator connected to it, and that's the reason why voltage magnitude becomes known, because from active power loss minimization voltage settings could be obtained. But the PG value is not chosen from economic dispatch for this swing bus or angle reference bus is because if we were to get all our generators or generation values from economic dispatch for different demands, then since we have done economic dispatch, load forecasting has given us all demands. So for this particular value of demand, okay, economic dispatch has given us the best possible value. But is it always feasible to do economic dispatch? Probably not. But on the other hand, the load can always change in time. It is a time varying quantity. Load doesn't remain fixed. So does it mean that every time one has to do economic dispatch in every microsecond, millisecond, nanosecond possible? No, it's not possible. If the load is changing and economic dispatch cannot be done, there has to be one generator which can account for this change in demand. That is point number one. The other aspect is, since the load is changing, the active power loss would also change. So there has to be one generator which is the generator of the swing bus, which is intently not specified, because if all PGs were to be given based on the fact that economic dispatch was recently done, then for a change in load, there is no guarantee that all generation would match the load entirely. Second, system loss is not a known quantity. I mean, by system loss, I mean both the active power loss and the reactive power loss. Active power loss and reactive power loss, they tend to happen in transmission lines. So active power loss is basically I square R loss. R is the line resistance, and reactive power loss could be inferred as I square X loss, where X is the line reactance. In fact, active power loss is the most critical loss which needs to be considered. Before we solve power flow equations, we don't know what the voltage phasors are. If we don't know what the voltage phasors are, we'll not be able to know what is the current flowing through a transmission line. If the current cannot be known, how do I know what is the value of I square R? And remember, generator need not only satisfy the load. Generator portion, some portion of generation also gets consumed as this active power loss. Before solving power flow, if we don't know what this loss is, then how do we ensure total generation should be equal to demand plus loss? So that's the reason why system loss is also not known. So slack bus or the swing bus, the term slack here, it accounts for any generation load mismatch and any system loss that would happen as the load is changing with respect to time. So I hope I have tried to explain the notion behind angle reference bus, because angle is chosen for the sake of finding our other voltage phase angles. The bus is also called as swing bus because we assume one of the generator buses to be this swing bus or slack bus, and slack comes in for the fact that the slack bus accounts for any power mismatch between generation and load and system losses. So essentially PGI and QGI, they are not specified for a slack bus or angle reference bus. In fact, ideally speaking, the slack bus should have infinite reactive power generation capacity. So generally one of those buses which is the largest, which is connected to a largest generator, is chosen as the slack bus. Min and max limits of QG are assumed to be infinite so that the voltage magnitude can always remain fixed. If it is not chosen, then what would be the problem? Like the way we would have difficulty finding the actual phase angles from voltage phase angle differences. If one of the voltage is not chosen as a reference, usually what would we expect? We would expect that in per unit analysis, if our voltage bases are chosen properly, voltage magnitude should be a number close enough to 1 per unit. If we don't specify this or let power flow know, okay boss, what is the 1 per unit reference that you are trying to find? So basically, if the voltage reference is also not known like angle reference, we would have a hard time finding voltages in power flow analysis, because there would be no reference of 1 per unit going into power flow module. 1 per unit is not a sacrosanct number. I'm just trying to convey that if the power flow gets to know, okay, what are the typical voltage numbers that should come in, then probably the power flow equation would be easier to solve. Similar is the case. So basically, with no voltage reference, it would become like that the all bus voltages are floating with respect to ground or neutral, and there is no unique voltage magnitude which can be obtained for such cases. So essentially, to summarize, slack bus or angle reference bus or swing bus has no power flow equations associated to it in power flow analysis, because for slack bus or angle reference bus, the voltage magnitude and phase angle are known a priori. There are no unknowns involved at all. So this table here or this slide here essentially summarizes the equations and unknowns involved for a n-bus power network. For a n-bus power network, if there are nd number of PQ buses and ng number of generator buses, out of which one bus is acting as the slack bus or swing bus or angle reference bus. So essentially, the effective number of PV buses is ng minus 1, where ng plus nd, it is equal to capital N being the number of buses in the power network. Then for each of these types and number of buses, the associated known quantities or specifications, they are given in the third column of the table. The equations to be solved for power flow, their numberings are also mentioned. The number of unknowns, if we count, that is for a PQ bus, there are P and Q equations. So each P and each Q result into NDP and NDQ equations. The number of unknowns are voltage magnitude and phase angle, which are again ND cross 1 vector and ND cross 1 vector pertaining to every such PQ bus. So there is a sort of consistency between the number of equations and number of unknowns for every PQ bus. For PV bus, we have only one equation for every PV bus. So basically, we have Ng minus 1 PV bus equations. The number of the unknowns are only the voltage phase angles, because voltage magnitude is known. So here again, it is Ng minus 1 cross 1 vector, which is consistent with the number of equations present for every such PV bus. So basically, there is a matching between the number of unknowns and number of equations, which can be solved by any technique at hand. And after we solve these equations and get these unknowns, we can then use these to evaluate the remaining quantities like reactive power generation for PV bus, real and reactive power generations at slack bus, real power flows, active power loss, etc., etc. So the next few set of slides, they essentially enumerate what is done after power flow is solved. We have still not seen how power flow equations are to be solved. We have only looked at the structure of these equations, and we'll see from the next lecture onwards how these equations can be solved. By the way, just to sort of emphasize another aspect before I forget, in context of slack bus or swing bus, we said that if one of the voltage magnitude references is not available, then power flow will have a hard time figuring out what should be the number of voltage magnitude which should come in. Indication or another analogy of this comes from the fact that if I look at my individual power flow equations, in each of these power flow equations with voltages as polar coordinates, the equations are quadratic equations in terms of voltage magnitude. So these are actually nonlinear equations, they are not linear equations. And the moment I have nonlinear equations or quadratic equations, every quadratic equation can have two unique roots. By root, I mean the value of voltage or unknown at which the effective equation becomes equal to 0. In a quadratic equation where there can be two possible roots possible, the logical value of those voltages could be any two random numbers. Typically, we call those to be low voltage solution and high voltage solution. Probably in the last module, if time permits, I'll explain why low voltage solution is not a desired solution and high voltage solution is the expected natural operating point for every power network. And this high voltage solution is a solution wherein voltages are around 1 per unit. There's a typical range in which these voltages can vary. Typically, that is around 0.8 to 1.2 or 1.9 to 1.1 per unit. So, with high voltage solution acting as a reference for the corresponding power flow equations, we can expect our solution to be a high voltage solution, which is the practical operating condition. If voltage reference is lost, then power flow equations will not be able to dictate whether the solution is going towards a low voltage solution, which is an impractical solution, or theoretically it is possible, but practically it is not going to operate because the network will not be able to operate at low voltage solution. So, by low voltage, if I were to say, let's say our voltage becomes equal to 0 per unit. So, basically all our power network, it is solidly grounded. If generator is trying to feed power from generating stations to load ends, the power will not go to the loads, they would actually flow into the ground or terminal with no overall effective utilization. So, once power flow analysis is done, voltage phases are known, line flows can be evaluated, line flow SIK, where so basically this is the complex power flowing from bus I to bus K on line connecting buses I and K. This is the complex power, which can again have its real and imaginary part P and Q, which is equal to product of voltage of bus I into conjugate of current through bus I and K through line IK. And that current is again a function of voltage difference plus the component of half-line charging susceptance, which is coming in because of the nominal pi model of line between buses I and K. YIK is the series line admittance, which again has a real part and imaginary part, and BSIK by 2 is the half-line charging susceptance. This expression can be again expanded in terms of actual voltage magnitudes and phase angles, which are known from the corresponding power flow solution. So, please verify the correctness of these equations. On similar lines, slack bus power generations can also be evaluated given that everything is now known. So, we can find the corresponding real power and reactive power slack generations at every buses. These are the injections, and then every injection should be equal to the generation minus demand. So, we can alternatively make use of generation values to find the corresponding generation at the slack bus generators. Similarly, we can also find the corresponding currents through every such line, using which we can find the corresponding I square R loss and also I square S loss, which I have not mentioned, although I square R loss can be found at every line, which when added gives us the system loss. The system loss is also equal. So, basically, if I were to mention here that by power flow, we are ensuring that PI should be equal to PGI minus PDI for all buses in the power network. And if I add all these equations, so here I would get PI I is equal to 1 to N should be equal to PGI minus summation PDI, I varying from 1 to N, I varying from 1 to N. This term here in a way represents total real power generation, which is happening in the network, whereas this term here represents total real power load in the network. And if total generation is not exactly equal to the total real power load, then the difference here has to be the total real power loss, which is happening in the transmission lines as I square R loss. So, by different ways, We can also find the power loss which is happening in both the real and reactive perspective in the power network, because we know all the voltage magnitudes, we know the currents, so we can sort of exclusively find these corresponding loss components. Similar equations also exist for rectangular coordinates. I'll just cursorily go through them. The voltage is now expressed in terms of rectangular coordinates. So therein you can sort of separate out the corresponding real and reactive power injection equations. Associated real and reactive power flows on lines can also be evaluated on similar lines. In fact, if you compare the previous slide, which is slide number 10, you can substitute these numbers. So Vi mod square, or in a way alternatively, if you recollect, Ei, which was the real part of Vi phasor, it was equal to Vi cos theta as per the initial few slides that we saw, and Fi was imaginary part of Vi, which is Vi sin theta I. If I square up Ei square and Fi square, they essentially should be equal to Vi mod square, because cos square theta plus sin square theta is equal to 1. So Vi square can be replaced as Ei square plus Fi square. Is there a similar term appearing in rectangular version of real power flows? Yes, it is appearing similarly over here. So essentially you can substitute Vi cos theta, Vi sin theta by E's and F's respectively and get these numbers also. Slack bus power generations, they can also be evaluated. Since in slack bus power, for slack bus, the voltage magnitude is specified, voltage phase angle is 0. So F for slack bus, which is V sin theta. If theta is chosen as 0 degrees, F would be 0, and that's the reason why FSL, SL representing slack bus, becomes 0. The corresponding real part of voltage is same as the voltage magnitude. And on similar lines, you can find the corresponding real and reactive power generations of the slack bus in rectangular coordinates, and same also holds true for the active and reactive power loss. That's all for today's lecture. We will take up one common or well-known technique known as Gauss-Seidel method to understand how it can solve our nonlinear power flow equations. Thank you.